What if we're not alone in the universe? For centuries, that question has haunted scientists, dreamers, and stargazers alike, fueling our imagination with visions of distant worlds and civilizations beyond our own. But today, we're no longer just wondering. Thanks to cutting-edge telescopes and bold missions, we've uncovered real places beyond our solar system where life might actually exist. Picture this: 25 alien worlds, each with its own secrets, orbiting faraway stars. Some have oceans of liquid water hidden beneath icy shells. Others bask in the glow of twin suns, their skies painted in colors we can't even name. These aren't science fiction. They're exoplanets, real, verified, and teeming with possibilities. The hunt for these worlds is more than just a scientific achievement. It's a revolution in how we understand our place in the cosmos. Every discovery shakes the foundations of what we thought was possible. Take, for example, a planet like K2-18b, a watery super-Earth with an atmosphere that might just hold the ingredients for life. Or LHS-1140b, a rocky world locked in a dance with its dim red star, where the conditions could be just right for something extraordinary to thrive. These aren't just dots on a star map, they're potential homes for life as we know it, or even life as we don't. So how do we find them, and what makes these 25 worlds so special? That's where the story gets even more thrilling. From advanced telescopes peering into the depths of space to breakthroughs in how we detect faint whispers of atmospheres billions of miles away, the tools we're using are rewriting the rules of discovery. And the best part, we're just getting started. Each of these worlds is a puzzle waiting to be solved, a mystery begging to be unraveled. Some might be harsh and unforgiving. Others could be havens unlike anything we've ever seen. But one thing's for certain, the search for life out there changes how we see life right here. So let's dive in, because the universe is far stranger and far more wonderful than we ever dared to hope. Closest to us in the cosmic neighborhood, just over 4 light-years away, orbits a world that could rewrite our understanding of habitable planets. Proxima Centauri b, a rocky planet with a mass eerily similar to Earth, circles the faint red glow of Proxima Centauri, the nearest star to our Sun. Nestled in what astronomers call the habitable zone, this distant world sits at the perfect distance where temperatures might allow liquid water to pool on its surface. Picture an Earth-sized puzzle wrapped in the tantalizing possibility of oceans, continents, or even an atmosphere. But here's where the story takes a twist. Proxima Centauri is no gentle sun. It's a flare star prone to violent outbursts that blast its planets with radiation powerful enough to strip away atmospheres and scald surfaces. So could life survive such chaos? Scientists are torn. On one hand, the planet's Earth-like mass hints at a solid surface, and its orbit suggests temperatures that might keep water liquid if it exists. Some models even suggest that a thick atmosphere or a global magnetic field could shield the planet from its star's fury. On the other hand, those relentless flares might have already turned Proxima Centauri b into a barren wasteland, its potential for life seared away by relentless storms of stellar radiation. Yet hope isn't lost. Life on Earth thrives in extreme places, deep in ocean vents, buried under ice, even in the heart of radioactive waste. If organisms here can endure such harshness, why not there? The intrigue doesn't end with the science. Proxima Centauri b is more than a candidate for life. It's a testing ground for our future. Breakthrough Starshot, a visionary project, aims to send tiny probes there within our lifetime, skimming past at a fraction of light speed to snap photos and relay data. Imagine the first close-up of an alien world, one that might hold answers to humanity's oldest question. Until then, telescopes scour its faint light for traces of water, oxygen, or even industrial pollutants, hints of something or someone calling that turbulent world home. Proxima Centauri b reminds us that the universe loves irony. the closest Earth-like planet might also be the most perilous, and that's what makes it unforgettable. Proxima Centauri b challenges everything we thought we knew about where life could take hold. Locked in a tight orbit around its red dwarf star, this world likely faces tidal locking, a phenomenon where one side perpetually bakes in sunlight while the other plunges into eternal night. Picture a planet divided, a scorching hemisphere where temperatures could melt lead, and a frozen wasteland shrouded in darkness. Yet between these extremes, along the thin twilight zone where day meets night, conditions might just be temperate enough for liquid water to exist. It's in these marginal spaces that life could carve out a foothold, adapting to gradients of heat and cold unheard of on Earth. Atmosphere is the wild card here. If Proxima Centauri b has managed to retain a thick envelope of gases despite its star's violent flares, it could redistribute heat across its surface, softening the harsh divide between day and night. Some models suggest winds racing at supersonic speeds might carry warmth from the sunlit side to the dark, creating pockets of stability. Others propose a global ocean beneath layers of ice, sealed away from stellar radiation but kept liquid by geothermal vents, much like the hidden seas of Jupiter's moon Europa. The possibilities ignite the imagination. Could organisms here evolve to migrate with shifting temperature bands, or thrive in deep subterranean networks shielded from the surface's extremes? Then there's the question of time. Red dwarfs burn for trillions of years, far longer than stars like our Sun. If life did arise here, it would have had epochs to adapt, to radiation, to erratic stellar weather, to a world without seasons. Evolution under such conditions might produce life forms with biochemistries we can scarcely conceive. Microbes that repair DNA damage in real time, or organisms that draw energy from infrared light rather than visible sunlight. The very rules of biology could be rewritten, yet for all its promise, Proxima Centauri b remains a riddle. Without direct observations of its atmosphere, we're left reading shadows, interpreting the faintest clues in the light that reaches us across 4.37 light-years. Future telescopes like the James Webb Space Telescope's successors could analyze the chemical fingerprints of its skies, hunting for methane, oxygen, or even artificial pollutants. Every piece of data will bring us closer to answering whether this turbulent world is a cautionary tale, or proof that life clings on in the most unexpected places. One thing's certain, Proxima Centauri b isn't just a scientific curiosity. It's a mirror forcing us to rethink the boundaries of resilience, adaptation, and what it truly means to be alive. While Proxima Centauri b teases us with its turbulent potential, another world just 39 light-years away offers a completely different vision of what alien life might look like. Welcome to TRAPPIST-1e, a rocky exoplanet so eerily Earth-like in size and temperature that it tops the list of possible havens for life beyond our solar system. Nestled in the TRAPPIST-1 system, this fascinating world orbits an ultra-cool dwarf star, bathed in perpetual twilight hues of deep red and burnt orange. But what makes TRAPPIST-1e truly special isn't just its prime real estate in the habitable zone, it's the neighborhood it shares with 6 other planets, all packed closer together than Jupiter's moons. Think about that for a moment. If you stood on the surface of TRAPPIST-1e, some of its sibling planets would appear larger in the sky than our moon does from Earth. They'd drift by like slow-moving celestial giants, their atmospheres, if they have any visible to the naked eye. This isn't just a single world with potential for life. It's an entire compact family of planets, each with its own mysteries. Some might be barren rocks, while others could hide vast subsurface oceans, but TRAPPIST-1e stands out. With a diameter just 6% smaller than Earth's and a likely rocky composition, it hits the sweet spot. Not so massive that its gravity crushes the chance for life, and not so small that it loses the atmosphere needed to nurture it. Then there's the star itself. TRAPPIST-1 is a dim, cool ember compared to our Sun, but that's not necessarily a bad thing. planets orbiting it can huddle much closer without being scorched, meaning years on TRAPPIST-1e pass in just 6 Earth days. This proximity raises wild possibilities like tidal heating, where gravitational forces from the star and neighboring planets flex TRAPPIST-1e's interior, generating enough warmth to keep underground water liquid even if the surface freezes. But the real magic lies in what we haven't seen yet. Scientists are racing to analyze the atmospheres of these worlds for signs of water vapor, carbon dioxide, or even methane gases that could hint at geological activity or just maybe biological processes. Imagine discovering not just one habitable planet, but a network of them, all within shouting distance of each other. Could life hop between these worlds on meteorites, as some theories suggest happened in our own solar system? Or does each planet harbor its own unique experiment in biology? For now, TRAPPIST-1e remains a tantalizing blank canvas. Future telescopes will scrutinize its atmosphere for the chemical fingerprints of life, while missions like the James Webb Space Telescope continue peeling back layers of its secrets. Whether this world is a desert, a water world, or something beyond our imagination, one thing is clear. In the cosmic hunt for life, TRAPPIST-1e isn't just a candidate. It's a revolution waiting to happen, and it challenges us to think bigger, because if life can flourish here in this tightly packed planetary dance, then the universe might be far more crowded than we ever dreamed. The TRAPPIST-1 system doesn't just challenge our expectations, it shatters them. Here's why: 7 Earth-sized planets, each locked in an intricate gravitational ballet around their dim red star, so close together that a person standing on one could see the cloud patterns of another with the naked eye. But the real magic lies beneath the surface, literally. Tidal forces in this system don't just shape orbits, they might be the invisible engine powering entire ecosystems. Take TRAPPIST-1e, the crown jewel of the system. Unlike Earth, warmed by sunlight alone, this world could owe its habitability to relentless gravitational squeezing. Every time it passes a neighboring planet or tugs against its star, friction deep inside its rocky mantle generates heat, enough perhaps to melt underground ice into vast hidden oceans. Then there's the atmosphere problem, or rather, the atmosphere opportunity. In most planetary systems, losing an atmosphere to cosmic radiation is a death sentence. But in TRAPPIST-1, the planets orbit so close that their atmospheres might bleed into one another. Imagine a scenario where hydrogen, oxygen, or even organic molecules drift between worlds, carried by stellar winds or shared magnetic fields. A molecule exhaled by a microbe on TRAPPIST-1f could, over millennia, end up raining down on TRAPPIST-1g. It's a tantalizing thought. Life in this system might not be confined to a single planet. It could be a communal affair, but let's pause on that word, life. What would it even look like here, with perpetual twilight and a star emitting mostly infrared light? Photosynthesis as we know it might not work. Yet life is ingenious. Deep in Earth's oceans, organisms thrive near hydrothermal vents using chemosynthesis, a process independent of sunlight. On TRAPPIST-1e, evolution might have crafted organisms that harness geothermal heat or the faint glow of their star's infrared radiation. Their cells could pulse with exotic biochemistry, their metabolisms tuned to rhythms we've yet to imagine. And then there's the ultimate question: if life exists here, could it be intelligent? The planets are so close that a civilization on one might eventually launch probes, or even passengers, to another. Over cosmic timescales, life could spread like dandelion seeds in a breeze, hopping between worlds without ever needing interstellar travel. Of course, this is speculation, but that's what makes TRAPPIST-1 so electrifying. It forces us to rethink not just where life might exist, but how it might move, adapt, and communicate across an entire mini-solar system. For now, the answers hover just out of reach. Telescopes are hunting for atmospheric clues, oxygen, methane, or even industrial gases that could betray the presence of technology. Every new observation peels back another layer of this cosmic onion, revealing not just one world but a network of possibilities. The TRAPPIST-1 system isn't just a collection of planets. It's a challenge to our Earth-centric view of life, and with each discovery, the universe whispers back, "You haven't seen anything yet." 600 light-years from Earth, orbiting a star slightly cooler and redder than our Sun, a world named Kepler-442b spins in quiet defiance of the odds. This isn't just another exoplanet lost in the cosmic crowd. It's a super-Earth with a tantalizing resume. Roughly 1/3 larger than our home planet and nearly twice as massive, its gravity would feel crushingly different to a human visitor. Yet despite the extra weight, what makes this world extraordinary isn't just its size, it's where it lives. Nestled in the sweet spot of its star's habitable zone, Kepler-442b receives just enough light to keep water liquid, while its K-type host bathes it in a gentler, more stable glow than our own Sun's sometimes fiery temper. But life here would unfold on a different rhythm. A year on this world lasts 112 Earth days, short enough that you'd celebrate birthdays 3 times annually, yet long enough to hint at seasons unlike anything we know. And that heavier gravity, it could be a hidden blessing. A denser atmosphere might cling more stubbornly to the surface, shielding the planet from cosmic radiation and trapping heat more efficiently. Picture vast, shallow seas rippling under amber skies, their waves pulled into strange, slow-motion crests by the relentless tug of that stronger gravity. Plants, if they exist here, might grow sturdier, their stems thicken to withstand the constant downward press. Yet the star itself holds secrets. K-type stars like Kepler-442b's host are the Goldilocks of the cosmos, not too hot, not too cold, but just right for longevity. These stars burn for tens of billions of years, far outlasting our Sun. If life took root here, it would have had millennia to evolve, adapt, and perhaps even thrive in ways we can't yet fathom. Compare that to Earth's frantic biological timeline, and the possibilities stretch into awe-inspiring territory. The real kicker, Kepler-442b scores higher on Earth Similarity Index assessments than almost any other known exoplanet. It's not just the temperature or the orbit, it's the potential chemistry. Models suggest it could have a rocky composition rich in iron and silicates, with active geology recycling nutrients essential for life. Some scientists speculate its core might still churn with tectonic energy, driving volcanoes or hydrothermal vents that could serve as incubators for biology. Of course, mysteries linger. We don't yet know if this world has an atmosphere or whether its rotation locks one face eternally toward its star, creating a scorching day side and a frozen night side. But that's what makes it so compelling. Kepler-442b isn't just a scientific curiosity, it's a mirror held up to our own planet, asking us to reconsider what Earth-like truly means. In this distant, heavier world, we might find the most profound truth of all, that life, in its infinite creativity, could flourish under skies we've never seen, in rhythms we've never felt. And that changes everything. Deep in the constellation Cetus, 49 light-years from Earth, a planet named LHS 1140b defies expectations. This isn't just another rocky world, it's a super-Earth with a twist, a place where the usual rules of exoplanet habitability might not apply. Nearly 7 times heavier than our home planet, it orbits a dim red dwarf star so faint you'd need a telescope just to spot it. But what makes this world extraordinary isn't its size or its star. It's what scientists suspect hides beneath its frozen surface, a global ocean sealed under miles of ice but possibly teeming with the ingredients for life. Unlike many exoplanets around volatile red dwarfs, LHS 1140b enjoys a rare gift: stability. Its star is unusually quiet for its type, sparing the planet from the brutal radiation flares that batter worlds like Proxima Centauri b. That means something precious could have endured here, an atmosphere thick enough to trap heat and maintain surface pressure even after billions of years. Picture an icy shell, cracked by geysers spewing water vapor into a sky tinged orange by the dim glow of its sun. Below, tides from the star's gravity might flex the ice, generating enough warmth to keep a subsurface ocean liquid, an alien version of Europa's hidden seas, but on a planet with a surface gravity strong enough to make every step feel like carrying a backpack full of rocks. Then there's the light. Red dwarfs emit mostly infrared radiation, invisible to human eyes, but life doesn't need sunlight as we know it. Around hydrothermal vents in Earth's deepest oceans, entire ecosystems thrive in perpetual darkness powered by chemical energy. On LHS 1140b, organisms might harvest warmth from the planet's own core or exploit minerals percolating up through cracks in the ice. Their biology could be utterly alien microbes with proteins stabilized by pressure, or creatures that navigate using magnetic fields instead of sight. The real kicker, this planet's thick atmosphere, if it exists, could be a goldmine for biosignatures. Unlike thinner atmospheres that vanish under stellar winds, LHS 1140b's might cling stubbornly, preserving traces of gases like methane or oxygen that could hint at life below. Future telescopes might even detect plumes of water vapor erupting through the ice, a tantalizing sign that something stirs in those dark, briny depths. Of course, mysteries remain. Is the ice shell 50 miles thick or 500? Does the ocean contact a rocky seafloor, rich in minerals, or is it isolated, a closed system where life would need to recycle every scrap of nutrients? We won't know until we peer closer, but that's what makes LHS 1140b so compelling. It's not just a candidate for life, it's a test of how creative biology can be when given the right mix of stability, secrecy, and time. And in that quiet darkness beneath an unbroken sheet of ice, the universe might be conducting an experiment we're only beginning to imagine. Hidden in the constellation Aries, just 12 light-years from Earth, orbits a world that might just be the ultimate cosmic hideaway, Teegardens Star B. Unlike the violent flares of Proxima Centauri or the crowded dance of TRAPPIST-1, this planet circles one of the quietest, most unassuming stars in our galactic neighborhood. With roughly the same mass as Earth, it's easy to imagine standing on its surface gravity tugging at your feet just like home, but under a sky washed in perpetual twilight. That's because Teegardens Star is a dim red dwarf, so faint it wasn't even discovered until 2003. Yet this tiny, cool star might be the perfect host for life, offering something rare in the cosmos: stability. What makes Teegardens Star B so intriguing isn't just its Earth-like weight, it's where it sits. Nestled snugly in the habitable zone, this world receives just enough warmth to keep water liquid if it exists. But here's the twist: its star emits barely 1% of our sun's visible light. You might assume that would make the planet a frozen wasteland, but physics has a surprise in store. Red dwarfs like Teegardens Star pump out most of their energy as infrared radiation invisible to our eyes, but potentially a powerful heat source. An atmosphere rich in greenhouse gases like carbon dioxide or methane could trap that infrared warmth, turning what should be a frigid rock into a world with surprisingly mild temperatures. Imagine a landscape where the air itself glows faintly with absorbed heat, and lakes of liquid water persist under a dim, burgundy sky. Then there's the question of time. Teegardens Star is ancient, possibly twice as old as our Sun, giving life an almost unimaginable head start. If biology took root here, it's had billions of extra years to evolve, adapt, and perhaps even complexify. Picture organisms with metabolisms fine-tuned to infrared energy, or ecosystems built around geothermal vents in a planet still warm from its formation. Life here wouldn't just be alien, it might be older than multicellular life on Earth, a living fossil from an era before our solar system even existed. But the real magic lies in what we don't know. Is Teegarden's star B tidally locked with one side forever facing its star? If so, life might huddle in the twilight ribbon between scorching day and endless night. Or does it rotate slowly, offering a more even distribution of warmth? Telescopes are already hunting for clues in the faint light that filters through its atmosphere, searching for hints of water vapor or oxygen. Every new observation peels back another layer of mystery, revealing a world that challenges our assumptions at every turn. Teegarden's star B isn't just another exoplanet. It's a lesson in cosmic humility, proof that the quietest corners of the universe might hide the most extraordinary possibilities. And as we stare into its dim red glow, we're left with a haunting thought. If life thrives here in such gentle obscurity, how many other hidden wonders are waiting to be found? Imagine stumbling upon a world almost exactly Earth-size, tucked neatly into the habitable zone of a distant star, a place where sunlight, though dimmer than our own, might still nurture life. That's Kepler-442b, a milestone in exoplanet discovery. When scientists confirmed its existence in 2014, it became the first Earth-sized planet ever found orbiting within the Goldilocks zone of another star, not too hot, not too cold, but just right for liquid water. Orbiting a cool, red dwarf star 500 light-years away, this planet is a tantalizing glimpse into how common or rare Earth-like worlds might be across the cosmos. But life here would unfold under a very different sky. Kepler-442b star emits most of its light in the infrared spectrum, bathing the planet in a deep, ruddy glow. To human eyes, the landscape might appear forever bathed in the hues of a perpetual sunset, with shadows stretching long and colors muted. Yet for potential organisms, this dim light could be more than enough. On Earth, certain bacteria and deep-sea corals thrive using infrared-sensitive pigments. If life exists on Kepler-442b, it might have evolved to harness this crimson light through a form of photosynthesis we've never seen, one that uses different wavelengths or chemical pathways to convert energy. Picture forests of alien vegetation, their leaves not green but perhaps black or deep purple, optimized to absorb every precious photon from their faint star. The star itself, though, poses both promise and peril. Red dwarfs are notorious for their volatility, frequently erupting with flares that could strip atmospheres and scour surfaces with radiation. Yet Kepler-442b orbits far enough out, with a year lasting 130 Earth days, that it might avoid the worst of these tantrums. Models suggest its atmosphere, if thick enough, could shield any life from the occasional stellar outburst. Even more intriguing, tidal forces from the star might keep the planet's interior warm, driving geologic activity that replenishes nutrients and stabilizes the climate over eons. Then there's the question of rotation. Is Kepler-442b tidally locked with one side forever day and the other endless night? Or does it spin slowly, offering a more even distribution of light and warmth? The answer could determine where life clings on. On a locked world, organisms might crowd the terminator line, the narrow band between day and night where temperatures are moderate. Alternatively, strong atmospheric currents could ferry heat from the sunlit side to the dark, creating habitable pockets across the globe. What makes this planet truly extraordinary, though, is its symbolism. Kepler-442b proved that Earth-sized worlds in habitable zones aren't just theoretical, they're out there, waiting to be found. It's a reminder that the ingredients for life might be scattered throughout the galaxy, hidden under alien suns, in colors and forms we're only beginning to imagine. And as we study its crimson skies and speculate about its landscapes, we're not just exploring a single world. We're glimpsing a universe of possibilities, one where life, in all its diversity, could be far more common than we ever dared to dream. 41 light-years from Earth, tucked into a quiet corner of the constellation Hydra, orbits a world that defies first impressions. GJ357d might sound like just another entry in the growing catalogue of exoplanets, but this super-Earth is anything but ordinary. Discovered in 2019 by NASA, a transiting exoplanet survey satellite, it immediately grabbed scientists' attention for one compelling reason. Even in the frigid outskirts of its star's habitable zone, this planet could harbor liquid water not on its surface, but hidden beneath a bizarrely thick atmosphere that acts like a cosmic pressure cooker. Picture a world where the air itself is the secret to survival. With a mass at least 6 times Earth's and a likely rocky composition, GJ357d basks in starlight weaker than what Mars receives from our Sun. On paper, that should make it an ice ball. Yet here's the twist: its crushing atmosphere, possibly dozens of times denser than Earth's, traps heat so efficiently that the surface could host pools of liquid water under the right conditions. Not sprawling oceans, but perhaps briny lakes nestled in volcanic valleys, kept from freezing by the sheer weight of the air above them. It's a scenario that turns our understanding of habitability on its head. The star at the heart of this system plays a surprising role. GJ357 is a modest red dwarf, far cooler than our Sun, but its gentle nature might be the planet's saving grace. Without the violent flares that plague many similar stars, GJ357d's atmosphere could have persisted for billions of years, long enough for chemistry to potentially brew the building blocks of life. Add in tidal heating from the star's gravity flexing the planet's interior, and you've got a recipe for underground hydrothermal systems where organisms could thrive far from the frozen surface. What really sets this world apart, though, is its discovery story. Unlike most exoplanets found through the transit method, watching for a star's dimming as a planet crosses its face, GJ357d was detected indirectly through tiny wobbles in its star's motion. That makes its existence all the more thrilling. We can't yet study its atmosphere or map its surface, but the very fact that we found it suggests something profound. For every exoplanet we spot, there could be dozens more lurking just beyond our current detection limits, each with its own secrets waiting to be uncovered. GJ357d forces us to expand our imagination. Life doesn't need Earth-like conditions, just a niche where liquid water, energy, and time intersect. Whether this distant world holds oceans under ice, steamy greenhouse lakes, or something stranger still, it stands as a testament to the universe's boundless creativity. And in that quiet corner of Hydra, a tantalizing question lingers. If life can find a way here, in such an unforgiving place, where else might it be hiding? Somewhere in the cosmos, suspended 110 light-years away, a planet named K2-18b challenges our very definition of habitable. This isn't just another exoplanet, it's a world where the atmosphere itself whispers tantalizing secrets. In 2019, astronomers made history when they detected water vapor swirling in its skies, marking the first time we'd found an alien world with both water and temperatures that could support life. But here's where the story gets even stranger. K2-18b doesn't fit the mold of a traditional Earth-like planet. It's what scientists call a hycean world, a term blending hydrogen and ocean, a place where vast global seas might slosh beneath a thick, hydrogen-rich atmosphere. Picture an environment unlike anything in our solar system. The surface, if it exists at all, could be utterly drowned beneath an ocean hundreds of miles deep, pressurized by an atmosphere so dense it behaves more like liquid gas than air. Under that crushing weight, water wouldn't boil even at temperatures far beyond Earth's limits, creating a bizarre realm where the very laws of physics feel alien. Yet within those depths, something extraordinary might be happening. Hydrogen-rich atmospheres are excellent at trapping heat, meaning the ocean below could be tepid, even cozy, a perfect nursery for life as we know it. But how could biology take root in such a place? Earth teaches us that life thrives in boundary zones, places where water, rock, and energy intersect. On K2-18b, hydrothermal vents on the seafloor could churn out nutrients, while organic molecules rain down from the atmosphere above. Microbes here might metabolize hydrogen instead of oxygen, or derive energy from chemical gradients created by the immense pressure. Some scientists speculate that hycean worlds could host entire ecosystems floating in their upper atmospheres, where temperatures and pressures are milder, like airborne plankton drifting in an endless sky sea. The implications are staggering. If life can flourish in such extreme environments, the galaxy might be teeming with hycean worlds, each a potential oasis in the cosmic desert. K2-18b orbits a cool red dwarf, a type of star that outnumbers Sun-like stars 10 to 1 in the Milky Way. That means there could be millions of similar planets waiting to be discovered, each with its own hydrogen-shrouded ocean. Yet mysteries remain. Does K2-18b's atmosphere contain traces of dimethyl sulfide, a gas produced almost exclusively by marine life on Earth? Future telescopes will hunt for this and other biosignatures, peeling back the layers of its alien skies. What we learn could redefine not just where we look for life, but what we look for. K2-18b isn't merely a scientific curiosity. It's a key, one that might unlock untold doors in our search for cosmic company. And as we stare into its murky, water-laden heavens, we're forced to ask, if life can take hold here in this crushing, hydrogen-soaked realm, then where can't it? The concept of hycean worlds flips the script on everything we thought we knew about habitable planets. Unlike Earth, where life thrives on a rocky surface under a nitrogen-oxygen sky, these alien environments rewrite the rules entirely. Picture a planet with no land at all, just an endless global ocean, dwarfing even Earth's deepest trenches, capped by an atmosphere so thick with hydrogen that the boundary between sea and sky blurs into a hazy, pressurized twilight. This is the hycean realm, where temperatures and pressures we'd consider lethal on Earth might be the norm for an entirely different kind of biology. K2-18b stands as the poster child for this radical theory, and for good reason. Its detection of water vapor was just the beginning. Recent studies suggest its hydrogen-rich atmosphere could act like a giant blanket, trapping enough heat to keep subsurface layers warm despite orbiting a cool red dwarf star. But here's where it gets even wilder. In such extreme conditions, the very chemistry of life might operate differently. On Earth, water dissociates into hydrogen and oxygen, but in a hycean world's depths, hydrogen could dominate reactions, creating organic compounds we've never seen. Microbes here might not breathe oxygen. They could metabolize hydrogen sulfide or even form symbiotic relationships with minerals spewing from underwater vents. What makes these worlds especially tantalizing is their durability. Hydrogen atmospheres resist stripping by stellar winds better than thinner ones, meaning hycean planets could stay habitable for billions of years longer than Earth. Imagine a microbial empire evolving uninterrupted across epochs. A slow, steady experiment in adaptation unfolding beneath skies where the sun is just a dim red ember. Yet K2-18b's greatest gift might be its detectability. That same thick atmosphere that makes it inhospitable to humans also amplifies potential biosignatures. Molecules like methyl chloride or dimethyl sulfide gases linked to life on Earth would accumulate in detectable amounts, giving telescopes clear targets. Future missions like the James Webb Space Telescope could scan its skies for these clues, turning speculations into hard data. The implications ripple far beyond one planet. If K2-18b proves hycean worlds can host life, the galaxy suddenly becomes far more interesting. Red dwarfs, the most common stars, might each host similar water-rich worlds, hidden oceans wrapped in hydrogen veils, waiting for their stories to be told. And as we peer into the steamy depths of K2-18b's alien seas, we're left with a humbling thought. The universe doesn't care about our definitions of habitable. Life, it seems, will find a way even in places we once wrote off as impossible. Among the countless exoplanets uncovered in recent years, TOI 700d stands out for its rarity, an Earth-sized world orbiting calmly in the habitable zone of a peaceful red dwarf star 100 light-years away. Discovered by NASA Transiting Exoplanet Survey Satellite, or TESS, in 2020, this planet shattered expectations. Most habitable zone exoplanets are either super-Earths or gas giants, but TOI 700d is different. At just 20% larger than Earth, it's one of the few known worlds where the gravity, sunlight, and temperature might feel familiar to life as we know it. What makes this discovery even more remarkable is the star itself. TOI 700 is a red dwarf, but unlike the volatile flare-prone varieties common to its class, this star is eerily quiet. Over 11 months of observation, TESS detected no violent outbursts, a stroke of cosmic luck that means TOI 700d might have retained its atmosphere over billions of years. That stability is crucial. Without the radiation storms that ravage planets like Proxima Centauri b, this world could have held onto its water, its air, and perhaps even the delicate chemistry needed for life to emerge. But the real magic lies in its orbit. TOI 700d completes a year in just 37 Earth days, circling close enough to its dim star that the sunlight it receives is comparable to what Mars gets from our Sun. At first glance, that might sound chilly, but here's the twist. Climate models suggest that with a thick enough atmosphere rich in greenhouse gases like carbon dioxide, the planet could trap enough heat to maintain liquid water on its surface. Some simulations even paint a scenario where TOI 700d is a water world, its entire surface glistening under a pale red sun with no land in sight. Then there's the question of rotation. Early data hints that TOI 700d might be tidally locked, with one side perpetually day and the other endless night. Yet this doesn't necessarily spell doom. Atmospheric currents could ferry warmth from the sunlit hemisphere to the dark, creating a twilight belt where temperatures are just right. Imagine a ring of perpetual dawn where oceans never freeze nor boil, and life, if it exists, clings to the balance between two extremes. TOI 700d's discovery also marks a triumph for TESS, a mission designed to scour nearby stars for exactly this kind of world. Unlike Kepler, which stared deep into distant patches of sky, TESS focuses on bright, nearby stars, making follow-up studies far easier. Already, astronomers are using other telescopes to analyze the planet's atmosphere for traces of water vapor, methane, or even oxygen. Every new observation brings us closer to answering the haunting question: could this quiet, Earth-sized world be harboring something extraordinary? Perhaps the most humbling thought is this: TOI 700d isn't alone. Its star hosts two other planets, though neither sits in the habitable zone. Yet their presence hints at a system that, in its own quiet way, mirrors our solar family. As we study this distant world, we're not just exploring a single point of light. We're glimpsing a template proof that Earth-sized planets in stable, life-friendly orbits might be scattered across the galaxy, waiting for us to find them. And in TOI 700d's gentle glow, we see something profound, the universe once again offering a whisper of possibility. Just 14 light-years from Earth, cosmically speaking, right next door orbits a world that could be one of our best shots at finding life beyond the solar system. Wolf 1061c isn't just another exoplanet lost in the vastness of space. It's a rocky super-Earth, roughly 4 times the mass of our home planet, circling a dim red dwarf star in what astronomers call the conservative habitable zone. That means it receives just enough starlight to potentially harbor liquid water without tipping into extremes of heat or cold. But here's the catch: this world dances on the edge of possibility, where even the slightest shift could turn it from a potential oasis into a sterile wasteland. Picture a planet forever caught between two realities. Wolf 1061c is likely tidally locked, meaning one hemisphere permanently faces its star, basking in eternal daylight, while the other is plunged into endless night. The day side might sizzle under a crimson sun, its surface temperatures hovering near the upper limits of what life could tolerate. Meanwhile, the night side could be a frozen wasteland where even gases like nitrogen freeze solid. But between these two extremes, along the thin ribbon of twilight where day meets night, conditions might be just right for water to pool and cling, a fragile sanctuary for any organisms that could adapt to such a stark divide. Yet the challenges don't stop there. Red dwarfs like Wolf 1061 are notorious for their mood swings, unleashing violent flares that bombard nearby planets with radiation. While Wolf 1061 is relatively calm compared to stars like Proxima Centauri, even occasional outbursts could erode an atmosphere over time, unless the planet has a robust magnetic field or geological activity to replenish lost gases. And then there's the question of seasons. Because of its elliptical orbit, Wolf 1061c might experience dramatic temperature swings as it swings closer to and farther from its star, creating cycles of scorching heat and bitter cold that could test the limits of resilience. But life, as Earth teaches us, is stubborn. In our own planet's harshest environments, acidic hot springs, radioactive waste pools, the crushing depths of the ocean, organisms find a way. If Wolf 1061c has retained an atmosphere, or if subsurface oceans lurk beneath its ice, life there might have evolved to migrate with shifting climate bands or thrive in underground refuges shielded from the surface's extremes. What makes this world truly tantalizing is its proximity. At just 14 light-years away, it's one of the closest potentially habitable exoplanets we've found, close enough that future telescopes could analyze its atmosphere for biosignatures like oxygen or methane. Imagine detecting the faint chemical fingerprints of alien life in our cosmic backyard. Wolf 1061c isn't just a scientific curiosity. It's a mirror held up to our own planet's fragility and tenacity. And as we study its twilight zones and turbulent seasons, we're reminded the universe doesn't owe us habitable worlds, but sometimes, against all odds, it offers us a glimmer of hope. 1,200 light-years from Earth, where the constellation Lyra stretches across the void, a frozen giant named Kepler-62f drifts in silent orbit around its orange-hued star. This isn't just another exoplanet, it's a world that defies first impressions. At nearly 1.4 times Earth's size, its gravity would feel noticeably stronger to a human visitor, pulling at your bones with every step. But the real surprise lies in its climate. Kepler-62f orbits at the frosty outer edge of its star's habitable zone, where sunlight is weak and diffuse, like a candle flickering in a vast cavern. A year here lasts 267 Earth days, long enough for seasons to unfold in slow motion under skies painted in perpetual twilight. Yet beneath its icy exterior, this world might hide a secret that rewrites the rules of habitability. Scientists suspect Kepler-62f could harbor a global ocean, sealed under a miles-thick shell of ice but kept liquid by heat bubbling up from the planet's core. Sound familiar? It's a scenario straight out of our own solar system, where moons like Europa and Enceladus hide subsurface seas despite being far from the sun's warmth. But Kepler-62f isn't a moon. It's a planet with geological forces that could dwarf those of any icy satellite. Imagine tidal flexing from its star churning the ocean depths, or hydrothermal vents dotting a dark seafloor, pumping out minerals that could fuel entire ecosystems. The difference: this alien ocean wouldn't be pocket-sized. It could span the entire planet, a watery abyss so vast it makes Earth's oceans look like puddles. The star itself plays a quiet but crucial role. Kepler-62 is a K-type dwarf, older, cooler, and more stable than our Sun. That means this planet has likely enjoyed billions of years of uninterrupted tranquility, free from the violent flares that plague younger red dwarfs. Time is the missing ingredient in so many habitability equations, and Kepler-62f has had plenty. If life exists here, it's had epochs to adapt to the darkness, to find energy in chemical gradients or geothermal heat rather than sunlight. Organisms might drift through those pitch-black waters, blind but exquisitely tuned to vibrations or temperature shifts. A biology sculpted by isolation and patience. Of course, mysteries linger. Without direct observations of its atmosphere or surface, we can't say for certain whether those subsurface oceans exist. But the math is compelling. Models suggest that with the right mix of insulating ice and internal heat, Kepler-442b's hidden seas could persist for billions of years. Future telescopes might one day detect telltale geysers erupting through cracks in the ice, or trace the chemical signatures of ocean minerals in its faint atmosphere. Until then, this distant world stands as a testament to the universe's creativity, proof that life's canvas extends far beyond the sunlit surfaces we know. And as we ponder its frozen shell and the secrets it guards, we're left with a humbling thought. Sometimes the most promising worlds aren't the ones that look like home. They're the ones that show us how much we still have to learn. HD 40307G isn't just another exoplanet, it's a cosmic paradox. This super-Earth, tipping the scales at 7 times the mass of our home planet, orbits a quiet orange dwarf star 44 light-years away. But what makes it truly extraordinary isn't just its size, it's the way it moves. Unlike Earth's nearly circular orbit, this world follows a stretched, elliptical path around its star, swinging dramatically closer and farther away over the course of its 200 Earth-day year. Picture a planet where seasons aren't just mild shifts in temperature, they're radical transformations. One moment, the surface could bask in a gentle warmth reminiscent of springtime on Earth. Months later, the same landscape might plunge into deep freeze as the planet hurtles to the far reaches of its orbit. For life, this pendulum of extremes would demand extraordinary resilience. On Earth, organisms adapt to seasonal changes, migration, hibernation, or shifting metabolic rates. But HD 40307G's fluctuations would dwarf anything we experience. During its summer, when the planet nears its star, surface temperatures could soar, evaporating shallow seas and forcing any life to retreat underground or into deep water. In winter, as it retreats to the orbit's outer edge, global oceans might freeze over, locking the planet in ice. Yet between these extremes, there could be sweet spots, periods where temperatures stabilize just long enough for life to flourish. Microbes might lie dormant for years, only to awaken during brief habitable windows, racing to reproduce before conditions turn deadly again. The planet's super-Earth status adds another layer of intrigue. With stronger gravity, any atmosphere would cling tightly, potentially buffering against the worst temperature swings. Thick air currents could redistribute heat, smoothing out the stark contrasts between orbital extremes. Some models even suggest that a hydrogen-rich atmosphere might act like a planetary thermostat, trapping warmth during the cold phases and reflecting excess heat during the scorching ones. Imagine a world where the sky itself is part of the survival strategy, a dynamic shield against the whims of its eccentric orbit. But the real question isn't just whether life could survive here, it's what that life would look like. Evolution under such erratic conditions might favor organisms with unparalleled flexibility. Think of creatures that alter their biology with the seasons, or ecosystems built around geothermal oases where underground heat provides a constant refuge. On Earth, tardigrades can survive near absolute zero and boiling temperatures by entering suspended animation. On HD 40307G, entire biospheres might operate on similar principles, cycling between activity and dormancy in sync with their unstable star. The irony, this world's very harshness could make it a prime candidate for detection. Wild climate swings might churn its atmosphere with detectable storms or chemical shifts, offering telescopes clearer biosignatures than those of more temperate planets. Future missions could scan for gases like methane or oxygen that fluctuate predictably with its orbit, hinting not just at life's presence, but at its remarkable adaptability. HD 40307G doesn't just challenge our definitions of habitability, it dares us to imagine life not as a delicate flame, but as a force that bends without breaking, even under the universe's most ruthless rhythms. GJ667cc isn't your average exoplanet, it's a world bathed in the glow of not one, not two, but three suns. Orbiting the smallest star in this trinary system, 22 light-years from Earth, this super-Earth sits squarely in the habitable zone where temperatures could allow liquid water to exist. But here's where things get fascinating. The other two stars in the system, a pair of orange dwarfs, circle farther out, casting their own faint light on GJ667c's skies. Imagine standing on its surface. During the day, a small crimson sun dominates the heavens, while at night, the distant duo might appear as brilliant twin beacons, bathing the landscape in an eerie, perpetual twilight. What does this cosmic trio mean for the planet's climate? Unlike single-star systems where seasons follow predictable patterns, GJ667c's weather could be a complex dance of competing influences. The primary star provides steady warmth, but the gravitational tug and occasional extra light from its companions might introduce subtle climate variations over centuries. Some models suggest these stars could stir up atmospheric currents, creating weather systems unlike anything on Earth, gentle global tides of wind and cloud that redistribute heat more evenly across the planet. Then there's the Earth Similarity Index, a scale that measures how closely an exoplanet mirrors our own world in size, temperature, and composition. GJ667cc scores an impressive 0.85 out of 1, making it one of the most Earth-like worlds we've discovered. With a mass roughly 3.7 times Earth's, its gravity would feel heavier but not unbearable, like wearing a weighted blanket at all times. Its rocky composition hints at familiar geology, possibly even plate tectonics that recycle nutrients and stabilize the climate over eons. But the real magic lies in its potential for habitability. Red dwarfs like GJ667c's primary star are notorious for flare activity. Yet this particular star is relatively calm, a rarity that increases the chances of the planet retaining a protective atmosphere. Combine that stability with the energy input from its stellar companions, and you've got a world where photosynthesis could evolve in unexpected ways. Plants here might adapt to harness light across a broader spectrum, from the deep red of the primary star to the amber glow of the distant twins, resulting in vegetation with wildly different colors, perhaps black or purple to absorb every available photon. Of course, mysteries remain. Is GJ667cc tidally locked with one side forever facing its star? If so, life might huddle in the twilight zone where temperatures are moderate. Or does it rotate, offering more evenly distributed conditions? Telescopes haven't yet detected its atmosphere, but future instruments could hunt for gases like oxygen or methane signatures that would transform this intriguing world from a scientific curiosity into a potential haven for life. GJ667cc challenges our assumptions about what makes a planet livable. Most habitable zone exoplanets orbit solitary stars, but this one thrives in a stellar family, proving that life's potential isn't limited to cosmic singles. And as we study its triple sun skies and Earth-like promise, we're reminded the universe doesn't follow our rules. Sometimes it hands us a world where the ordinary and the extraordinary collide, and that's where the real discoveries begin. Kepler-442b isn't just another exoplanet, it's a mirror held up to Earth's own future. Orbiting a star almost identical to our Sun, this distant world has earned the nickname Earth's cousin for good reason. Sitting snugly in the habitable zone of Kepler-442, a G-type star just 4% more massive and 10% brighter than our own, this planet receives sunlight eerily similar to what bathes our home. But here's what makes it truly remarkable. Kepler-442b has spent 6 billion years in that sweet spot, nearly 2 billion years longer than Earth. That's an unfathomable stretch of time for life to arise, evolve, and perhaps even flourish. Picture a world where biology has had a head start measured in epochs. On Earth, complex life took roughly 4 billion years to emerge from primordial ooze to technological civilization. But on Kepler-442b, evolution might have had an extra 2 billion years to experiment. Imagine ecosystems refined over spans so vast they make human history look like a blink. Forests with root systems spanning continents, organisms with metabolisms fine-tuned to cycles we can't yet comprehend, or even intelligence that's had millennia to ponder the cosmos. The sheer time this planet has enjoyed raises staggering possibilities. What does life become when given such an unimaginable runway? Then there's the star itself. Unlike the volatile red dwarfs that dominate exoplanet discoveries, Kepler-452 is a sun-like star in every sense. It burns steadily without the violent flares that strip atmospheres or scald surfaces. This stability means Kepler-452b could have retained its atmosphere, oceans, and climate for billions of uninterrupted years, a luxury most habitable zone exoplanets don't share. Models suggest its gravity, roughly twice Earth's, would help anchor a thick atmosphere, potentially rich in oxygen or other biosignatures. But the planet's age also presents a haunting question. If life did arise here, what stage might it be in now? Earth's own technological adolescence began just a few centuries ago. A civilization with a billion-year lead might have mastered energy sources, engineering, or even interstellar travel in ways we can't fathom. Or perhaps biology there took an entirely different path, one where intelligence never emerged, but where ecosystems reached complexity beyond anything in our fossil record. The possibilities are as exhilarating as they are humbling, yet for all its promise, Kepler-452b remains frustratingly out of reach. Located 1,400 light-years away, it's too distant for current telescopes to analyze its atmosphere in detail. We can't yet search for the chemical fingerprints of forests, oceans, or cities, but that doesn't diminish its significance. This world stands as a testament to the universe's patience, proof that somewhere out there, a planet like ours might have had the one thing Earth lacked, enough time to truly unfold. And in its ancient, sunlit skies, we catch a glimpse of our own potential future, one where life, given eons, might write stories we're only beginning to dream. Ross 128b offers something rare in the cosmic hunt for habitable worlds: peace. Orbiting a tranquil red dwarf just 11 light-years from Earth, this exoplanet avoids the violent tantrums of stars like Proxima Centauri, whose radiation flares could strip away atmospheres and scald surfaces. Instead, Ross 128b basks in the steady glow of one of the calmest red dwarfs, known a star so quiet that astronomers didn't detect a single flare during years of observation. That stability is a game-changer. While many potentially habitable exoplanets face constant bombardment, this world might have enjoyed billions of years of uninterrupted serenity, enough time for chemistry to simmer into biology under skies free from steroidal radiation. But what makes Ross 128b truly stand out is its location. Nestled snugly in the inner edge of its star's habitable zone, it receives only 38% more sunlight than Earth. That might sound scorching, but red dwarfs emit mostly infrared light, less energetic than the visible light bathing our planet. Climate models suggest that with a reflective cloud cover or a moderately thick atmosphere, Ross 128b could maintain Earth-like temperatures despite the extrastellar energy. Picture a world where the air itself acts like a finely tuned thermostat, scattering just enough heat to prevent a runaway greenhouse effect while keeping oceans liquid and landscapes temperate. Then there's the gravity question. Ross 128b is at least 35% more massive than Earth, meaning you'd feel noticeably heavier walking on its surface. But here's the twist, that extra heft could be a hidden blessing. Stronger gravity helps planets retain atmospheres over cosmic timescales, especially around stars prone to atmospheric erosion. Combine that with Ross 128 gentle nature, and you've got a recipe for long-term habitability, a world where air and water might persist for billions of years, giving life ample opportunity to emerge and evolve. The star's longevity adds another layer of intrigue. Red dwarfs burn for trillions of years, far outlasting sun-like stars. If life took root here, it would have had epochs to experiment with forms and functions beyond our imagination. Organisms might harvest infrared light through exotic pigments, or thrive in subterranean networks shielded from surface radiation. Some scientists even speculate that photosynthesis here could produce black vegetation, optimized to absorb every scrap of energy from that dim crimson sun. Yet mysteries linger. Is Ross 128b tidally locked with one side forever day and the other endless night? Or does it rotate slowly, offering a more even distribution of warmth? Telescopes are already hunting for clues in the faint light filtering through its atmosphere, if it has one. Detecting gases like oxygen or methane could transform this quiet world from a scientific curiosity into a frontline candidate for life. Ross 128b doesn't dazzle with extreme features or dramatic settings. Its power lies in its subtlety, a reminder that sometimes the best places for life aren't the loudest or brightest, but the ones that offer consistency, patience, and time. And in its silent skies, we might find the universe's most profound lesson. Endurance, not spectacle, could be the key to thriving among the stars. Gliese 581g is one of the most debated exoplanets in astronomy, a world that might not even exist. Discovered in 2010, this potential super-Earth sparked immediate controversy when some scientists questioned whether the data was just noise in the star's signal rather than proof of a planet. Yet if real, Gliese 581g could rewrite our understanding of habitable zones. Orbiting a dim red dwarf 20 light-years away, it's tidally locked, meaning one side bakes under eternal sunlight while the other languishes in endless night. But between these extremes lies the Terminator line, the razor-thin border where day meets dark. This twilight strip could host conditions just right for life, where temperatures balance between scorching and frozen. Picture standing in that eerie in-between zone. The sun would hover motionless on the horizon, casting perpetual golden hour light across a landscape that never sees dawn or dusk. Rivers might flow from the molten day side, carving channels through the Terminator before freezing solid on the night side. Atmospheric currents could funnel warmth from the hot hemisphere, creating pockets of stability where liquid water lingers. Scientists speculate that life here would cling to this narrow band, evolving to migrate with shifting temperature gradients or burrowing underground to escape surface extremes. Organisms might develop photosynthesis tuned to the star's dim red light or harness geothermal energy seeping from the planet's core. The debate around Gliese 581g's existence only adds to its intrigue. Initial observations suggested a gravitational tug consistent with a 7-Earth mass planet in the habitable zone, but later studies failed to confirm the signal. Some astronomers argue the original detection was an artifact of the star's own activity. Red dwarfs are notoriously turbulent, their flares mimicking planetary wobbles. Others stand by the discovery, pointing to subtle patterns in the data that still hint at an unseen world. This uncertainty makes Gliese 581g a ghost in the exoplanet catalog, potentially groundbreaking yet just out of reach. Even if real, this world would face staggering challenges. Red dwarfs like Gliese 581 are prone to violent flares that could strip atmospheres and bathe surfaces in radiation. A tidally locked planet might rely on a global magnetic field to deflect these storms or a thick atmosphere to redistribute heat and shield the surface. Yet if life did arise here, it would have had time red dwarfs burn for trillions of years, offering biology epochs to adapt. The enduring mystery of Gliese 581g forces us to confront a deeper question. How do we define habitability when the rules keep changing? A planet that seems hostile by Earth standards might, under the right conditions, harbor life in ways we're only beginning to imagine. And whether this world is confirmed or debunked, its legacy endures, a reminder that the universe's most compelling stories often lie in the gaps between what we know and what we dare to dream. Kepler-442b isn't just another exoplanet, it's as close to an Earth twin as we've found beyond our solar system. Roughly the same size as our home planet and receiving 75% of the sunlight Earth does, this distant world orbits within the habitable zone of a red dwarf star 300 light-years away. The numbers alone are startling. Its radius is just 6% larger than Earth's, and its equilibrium temperature, before accounting for any atmosphere, hovers near Earth-like values. If you could stand on its surface, the sunlight might feel familiar, though tinged reddish from its cooler host star. But here's where the parallels take a dramatic turn. Kepler-1649c star is no gentle giant like our Sun. It's a tempestuous red dwarf, prone to flares that can erupt with the force of thousands of atomic bombs, drenching nearby planets in lethal radiation. So how could life survive under such chaotic skies? The answer might lie in the planet's resilience. Earth teaches us that life is tenacious, thriving in places we once deemed uninhabitable: acidic hot springs, radioactive waste sites, the crushing pressures of deep-sea trenches. On Kepler-1649c, organisms could retreat underground or beneath thick ice sheets, shielded from the worst of stellar outbursts. Subsurface oceans, warmed by geothermal activity or tidal forces, might serve as refuges, much like the hidden seas beneath Europa's icy crust. Alternatively, a dense atmosphere rich in protective gases like carbon dioxide could scatter and absorb harmful radiation, creating a buffer between the surface and the star's fury. The planet's orbit adds another layer of intrigue. Kepler-1649c circles its star every 19.5 Earth days, close enough that tidal forces might keep its interior churning with geothermal energy. This heat could drive volcanic activity, replenishing the atmosphere with gases stripped away by flares or powering hydrothermal vent systems, potential incubators for life. Imagine microbes clustered around underwater vents, their metabolisms tuned to chemicals rather than sunlight, oblivious to the storms raging above. Yet the greatest mystery isn't just survival, it's adaptation. Red dwarfs burn for trillions of years, offering biology an eternity to evolve under stress. Life here might have developed radical repair mechanisms, like real-time DNA mending or proteins stabilized against radiation. Photosynthesis, if it exists, could rely on infrared light, with organisms sporting black or deep purple pigments to absorb every scrap of energy from that dim crimson sun. Kepler-1649c challenges us to rethink the boundaries of habitability. It's not a paradise, it's a battleground where life would need every advantage to endure. But in its struggle, we might find the universe's most profound lesson: that life isn't fragile. It's relentless, carving out niches in the unlikeliest of places. And as we study this world's turbulent skies and Earth-like promise, we're forced to ask, if life can cling on here in the teeth of such chaos, where else might it be waiting? HD 85512b isn't just hugging the inner edge of its star's habitable zone, it's dancing on a razor's edge between paradise and inferno. Orbiting an orange dwarf star 36 light-years away, this super-Earth weighs in at over 3.5 times the mass of our home planet, with gravity strong enough to crush a human visitor under its relentless pull. But here's the twist: despite its punishing bulk and proximity to its star so close that a full year lasts a mere 58 Earth days, this world might still cradle liquid water, thanks to a climate trick straight out of Earth's playbook: clouds. Picture an atmosphere so thick with vapor that it acts like a planetary sunshade. HD 85512b's position means it receives significantly more stellar radiation than Earth, enough to boil away oceans under normal circumstances. But with enough cloud cover, some models suggest at least 50% sunlight could be scattered back into space before it ever reaches the surface, cooling the planet just enough to keep temperatures in check. It's a delicate balancing act, one where the difference between a temperate world and a scorched wasteland hinges on the whims of weather. The planet's dense atmosphere plays a starring role in this drama. That extra mass doesn't just anchor the air, it supercharges atmospheric circulation, potentially creating storms of staggering scale. Imagine hurricanes that span continents or cloud decks so persistent they never fully dissipate, locked in place by gravity's unyielding grip. These aren't just meteorological curiosities, they're lifelines. On Earth, clouds regulate temperature by reflecting sunlight and trapping heat. On HD 85512b, they might be the only thing standing between biology and annihilation. Then there's the star itself, a quieter, more stable cousin to our Sun. Orange dwarfs like HD 85512 burn slower and live longer than Sun-like stars, offering their planets billions of extra years of potential habitability. That longevity is key. If life did arise here, it would have had ample time to adapt to the planet's extremes, perhaps evolving under skies where the Sun looms large and red, forever veiled by a shimmering blanket of clouds. Organisms might rely on infrared radiation penetrating the haze, or tap into geothermal energy seeping from a tectonically active crust, yet mysteries linger. Is the cloud cover consistent, or does it wax and wane with chaotic seasons? Does the planet's gravity compress its atmosphere into exotic states, creating layers where gases behave more like liquids? Telescopes haven't yet detected water vapor or other biosignatures here, but future instruments could peel back the layers of its soupy skies, searching for clues. HD 85512b isn't just a lesson in atmospheric science. It's a challenge to our assumptions. Habitability isn't just about distance from a star. It's about atmospheres that self-regulate, clouds that shield, and life that finds a way, even under skies that would seem at first glance utterly hostile. And as we study this heavy, hazy world, we're reminded the universe doesn't do simple. It does survival in the most unexpected ways imaginable. Only 12 light-years from Earth, Tau Ceti e spins in the glow of a star almost identical to our Sun, a yellow dwarf so similar in size and brightness that it tops the list of places we might find a true Earth analog. But here's where the familiar ends. This super-Earth, weighing in at nearly 4 times our planet's mass, straddles the inner edge of its star's habitable zone like a tightrope walker, balancing between scorching heat and temperate promise. Its orbit is so close that a full year flashes by in just 168 Earth days, bathing the planet in sunlight 30% more intense than what we experience. That extrastellar energy should, by all rights, turn Tau Ceti e into a Venusian hellscape, a runaway greenhouse world with oceans boiled dry and skies choked in carbon dioxide. Yet some scientists whisper another possibility. What if this planet is a volcanic paradise where geothermal fury and sprawling oceans collaborate to defy the odds? The debate starts with its classification. Is Tau Ceti e truly a super-Earth or something more exotic, a mini-Neptune shrouded in thick hydrogen layers? Current data leans rocky, but that's just the beginning. Models suggest its tumultuous interior, heated by both radioactive decay and tidal forces from its star, could drive geologic hyperactivity on a scale we've never seen. Picture lava flows wider than continents, erupting from fractures in a crust constantly reshaped by the planet's own internal heat. These eruptions might pump enough sulfur dioxide into the atmosphere to form reflective clouds, bouncing sunlight back into space and cooling the surface just enough to allow liquid water to persist. It's a delicate dance, too much volcanism, and the skies turn opaque with ash, too little, and the greenhouse effect runs rampant. But if the balance is right, Tau Ceti E could harbor shallow seas fringing its lava plains, their steam mingling with volcanic gases to create a hazy, primordial sky. Then there's the ocean question. With gravity nearly twice Earth's, any liquid water here wouldn't behave as it does on our planet. Waves would rise slower and crash harder, their movements weighted down by the relentless pull. Tides, driven by Tau Ceti's gentle but persistent tug, might slosh across basalt shorelines with methodical precision, eroding rock into bizarre, elongated formations over eons. And beneath those alien waters, hydrothermal vents could pump out minerals at staggering rates, fueled by the planet's churning mantle. These vents wouldn't just be oases for life. They might be factories churning out chemical building blocks at speeds that dwarf Earth's own deep-sea systems. But the wildest theory of all, Tau Ceti E could be what scientists call a steam world, a planet where the line between ocean and atmosphere blurs into a global sauna. With surface temperatures hovering near the boiling point of water, its seas might never fully condense into stable lakes. Instead, they'd exist in a perpetual cycle of evaporation and rainfall, creating a humidity so thick it presses down like a second gravity. Life here would need to adapt to a world where liquids and gases trade places daily, where organisms float between layers of mist and brine, harvesting energy from the stars' filtered light or the planet's own geothermal whispers. What makes this world so compelling isn't just its extremes, it's the reminder that habitability isn't a checkbox but a spectrum. Tau Ceti E forces us to ask, can life thrive in a pressure cooker, under skies laced with volcanic ash, in oceans that simmer rather than surge? Every new observation peels back another layer of mystery, revealing not just a single planet but a challenge to our Earth-centric assumptions. And as we stare across those 12 light years, we're left with a humbling thought. Sometimes the most alien worlds are the ones that hold up the sharpest mirror to our own. Kepler-442b isn't just another exoplanet, it's a masterclass in cosmic survival. Orbiting a dim red dwarf star over 700 light-years away, this world packs an Earth-like radius into a package that defies expectations. Its star, cooler and smaller than our Sun, bathes the planet in a perpetual crimson glow, offering just enough warmth to tease the possibility of liquid water. But here's the twist: Kepler-442b likely doesn't rely on sunlight alone. Tidal forces from its close orbit could be flexing its rocky interior, generating enough heat to sustain vast subsurface oceans, an entire ecosystem thriving in the dark, powered not by the sun, but by the planet's own restless geology. Picture a world where the surface is frozen solid, a silent wasteland locked under miles of ice. Yet beneath that barren shell, chaos reigns. The constant gravitational tug of war between planet and star churns the mantle, creating friction that melts ice into sprawling underground seas. These aren't mere pockets of water, they could be global, interconnected oceans, their depths stirred by hydrothermal vents spewing minerals and warmth into the abyss. On Earth, such vents are teeming with life tubeworms, blind shrimp, and microbes that thrive on chemical energy rather than sunlight. On Kepler-442b, evolution might have taken this a step further, crafting organisms perfectly adapted to a world without day or night, where the only light comes from the faint glow of molten rock. The planet's Earth-like size adds another layer of intrigue. With a radius just 12% larger than our home world, its gravity would feel familiar, a rare trait among potentially habitable exoplanets. That similarity raises tantalizing questions. Could a rocky world of this scale maintain plate tectonics, recycling nutrients between crust and mantle? If so, the interplay between tidal heating and geologic activity might create a self-sustaining engine for life, where underwater volcanoes and mineral-rich currents feed ecosystems entirely cut off from the surface. But the star itself can't be ignored. Red dwarfs like Kepler-442b's host are infamous for their volatility, often erupting with flares that scour nearby planets with radiation. Yet tidal heating offers a counterbalance. Even if the surface is sterilized by stellar outbursts, the oceans below, insulated by miles of ice, could remain untouched, their inhabitants oblivious to the chaos above. Life here wouldn't just survive, it might flourish, evolving in isolation over billions of years into forms we can scarcely imagine. The mysteries of Kepler-442b are far from solved. Without direct observations of its atmosphere or surface, we're left to speculate, but that's what makes it so compelling. This world forces us to expand our definition of habitable, to consider that life's requirements might be more flexible than we ever dreamed. And as we peer into its hidden depths, we're reminded, sometimes the most promising worlds aren't the ones that look like home. They're the ones that show us how much we still have to learn. GJ-1214b shatters every Earth-bound assumption about where life could take root. This distant world, orbiting a dim red dwarf 40 light-years away, isn't just covered in water. It's a planet where the very concept of surface might not exist. Scientists classify it as a water world, but that label doesn't do justice to the reality. Imagine an ocean so deep it swallows entire continents, with no land in sight, just endless liquid stretching down to depths where pressures reach millions of times greater than Earth's deepest trenches. Here, water doesn't behave as we know it. Near the core, molecules crush into exotic forms of ice, not the familiar crystalline kind, but strange phases like ice 7 or superionic ice, where oxygen atoms lock into a solid lattice while hydrogen ions flow like liquid metal. The atmosphere adds another layer of surrealism. GJ-1214b's skies aren't clear or even cloudy, they're a thick, steamy shroud, so dense the boundary between ocean and air blurs into a soupy twilight. Sunlight filters through this perpetual fog as a dim, diffused glow, barely reaching the surface, if you can call it that. Temperatures hover around 200 degrees Celsius, too hot for liquid water under Earth-like pressures, but here, the crushing weight of all that overlying water keeps the ocean from boiling away. It's a pressure cooker paradise where the rules of chemistry twist into alien configurations. Life in such an environment would need to play by radically different rules. Without solid ground, organisms couldn't cling to rocks or roots. Instead, they might drift suspended in the water column, like gelatinous siphonophores in Earth's oceans, but adapted to far harsher conditions. Some scientists speculate about floaters, organisms that harness gas pockets to navigate the abyss, or microbes thriving near hydrothermal vents where minerals spew from the planet's molten core. Others imagine even wilder possibilities, creatures with biology tuned to exploit the strange properties of superionic ice, drawing energy from the shifting lattice of hydrogen ions like a battery. The real mystery lies in the planet's formation. GJ-1214b shouldn't exist by traditional models. Its density suggests it's mostly water with a rocky core, but how did it retain so much liquid when similar worlds usually lose their volatiles to space? One theory points to a late-stage delivery, comets or ice-rich asteroids bombarding the planet after its formation, drowning it in a deluge that never evaporated. Another suggests it migrated inward from the cold outer reaches of its system, its original ice melting into an ocean under the star's growing warmth. What makes GJ-1214b so compelling isn't just its defiance of expectations, it's the way it forces us to rethink the fundamentals of habitability. Life doesn't need a rocky shoreline or a sunlit meadow. It might flourish in the crushing dark under skies where the very air is water and the ground is a myth. As we study this world's steamy shroud and hidden depths, we're left with a humbling realization. The universe's creativity outpaces our imagination. And somewhere in that endless ocean, beneath pressure that would flatten a submarine, nature might be conducting an experiment in biology unlike anything we've ever seen. Kepler-442b might look like Earth's twin at first glance, a rocky world barely 12% larger than our own, perched perfectly in its star's habitable zone where temperatures could allow liquid water to pool on the surface. But this exoplanet, orbiting a red dwarf star 470 light-years away, hides a brutal secret. Its sun is a cosmic arsonist, unleashing flares so powerful they dwarf anything our sun has ever produced. Imagine a stellar eruption 10 times stronger than the most violent solar storm ever recorded on Earth. Now picture that happening every few hundred days, bathing Kepler-442b in enough radiation to strip away atmospheres and scald surfaces. This isn't just a theoretical danger. Observations reveal that Kepler-442's flares can spike brightness by over 30% in mere minutes, bombarding the planet with X-rays and ultraviolet radiation at levels hundreds of times more intense than what Earth receives. For any potential life, the challenge would be relentless. An atmosphere, if one ever existed, might have been eroded to a thin whisper, leaving the surface exposed to the star's fury. Oceans could have boiled away eons ago, their vapors torn apart by stellar winds. Even underground refuges might not be safe. Repeated flares could penetrate deep into the crust, sterilizing subterranean niches where life might cling. Yet here's where the story takes a surprising turn. Kepler-442b's very violence might also forge pathways for survival. Some models suggest that a planet with a robust magnetic field generated by a churning molten core could deflect the worst of the radiation, shielding any remaining atmosphere like an invisible force field. Alternatively, frequent flares might trigger chemical reactions in the upper atmosphere, creating organic compounds that rain down to the surface, providing building blocks for life against all odds. The planet's Earth-like size adds another layer of complexity. With gravity similar to our own, it could retain volcanic activity, spewing gases to replenish what the star steals away. Picture a world where geothermal vents dot the landscape, their plumes of heat and minerals offering havens for extremophiles organisms that thrive in conditions lethal to most life. These wouldn't be the lush forests or vast oceans we imagine on habitable worlds, but something far more primal. Microbial mats clustering near hotspots, evolving at breakneck speed to outpace the star's wrath. Then there's the question of time. Red dwarfs burn for trillions of years, and Kepler-442b has likely endured this bombardment for billions. Life here, if it exists, wouldn't just adapt. It would weaponize resilience. Organisms might develop biofluorescent shields to absorb and re-emit harmful radiation, or evolve rapid DNA repair mechanisms that make tardigrades look fragile. Photosynthesis, if it occurs, could rely on infrared light peeking through the chaos, turning the planet's surface into a tapestry of black or deep purple vegetation, optimized to survive the apocalypse daily. Kepler-442b forces us to redefine habitable. It's not a paradise, it's a battleground where survival demands ingenuity at a molecular level. But in that struggle, we glimpse something profound: life's capacity to persist in the universe's harshest corners. As we study this scorched, storm-lit world, we're left with a humbling thought. The search for life isn't just about finding Earth's twins. It's about discovering how far life can bend before it breaks. And Kepler-442b is pushing those limits to the extreme. Lytton Star B isn't just another exoplanet. It's a cosmic anomaly defying the odds stacked against habitable worlds around red dwarfs. Orbiting one of the quietest and most stable stars in our galactic neighborhood, this super-Earth sits just 12 light-years away, a stone's throw in cosmic terms. What sets it apart isn't just its proximity, but its Earth Similarity Index score of 0.91, placing it among the top contenders for a world that could feel eerily familiar. Picture a planet with a likely rocky composition, bathed in the gentle crimson glow of its host star, a dim red dwarf so calm it makes our sun seem temperamental by comparison. The star's serenity is Lytton Star B's greatest gift. Unlike the violent flares of Proxima Centauri or TRAPPIST-1, this star emits barely a flicker of disruptive activity, offering its planet something rare in the cosmos: consistency. Over billions of years, that stability could have allowed Lytton Star B to retain a thick atmosphere, nurture liquid water, and perhaps even foster the delicate chemistry of life. Climate models suggest its surface temperatures might hover near Earth-like averages, especially if clouds or greenhouse gases help distribute warmth across its tidally locked hemispheres. But the real marvel lies in how life here might adapt to its perpetually dim skies. The star's light peaks in the infrared spectrum, invisible to human eyes but potentially a goldmine for organisms tuned to harness it. Photosynthesis on Earth relies on visible light, but plants on Lytton Star B could evolve entirely different pigments, black or deep purple, to absorb every scrap of infrared energy. Imagine forests where leaves shimmer like obsidian, their cellular machinery optimized for a sun that never burns bright. Or consider the possibility of organisms blending multiple energy sources, supplementing starlight with geothermal heat from tidal forces flexing the planet's interior. The planet's tidal locking adds another layer of intrigue. One side forever faces its star, basking in eternal twilight, while the other remains cloaked in endless night. Yet atmospheric currents could ferry warmth across the terminator line, creating habitable ribbons where temperatures allow rivers to flow and chemistry to stir. Subsurface oceans might lurk beneath ice sheets, shielded from stellar winds and pulsing with hydrothermal activity. Lytton Star B challenges our Earth-centric biases. It's a world where biology, given enough time and stability, might craft solutions we've yet to imagine. Future telescopes could scan its atmosphere for oxygen, methane, or even artificial lights, hints that this tranquil world holds more than just potential. It might hold proof that life, when handed the right mix of patience and peace, can flourish under the quietest of suns. Kepler-442b isn't just a lone wanderer. It's part of an intricate 5-planet family, each member locked in a delicate gravitational dance around a dim, cool star. This Earth-sized world, orbiting firmly within its system's habitable zone, offers something rare: the chance that life might not be confined to a single planet. Picture a cosmic archipelago where shared atmospheres or even moons could become stepping stones for biology. Kepler-442b's star emits barely 5% the visible light of our Sun, but its gentle glow might be enough to sustain liquid water on surfaces or in subsurface layers across multiple worlds in the system. Orbital dynamics here are a masterclass in cosmic harmony. The 5 planets are packed tighter than Jupiter's moons, with Kepler-442b completing a full orbit in just 34 Earth days. Such proximity raises a tantalizing possibility: atmospheric exchange. Stellar winds or gravitational nudges could strip gases from one planet and deposit them onto another, seeding atmospheres with water vapor, methane, or even complex organic molecules. Imagine a scenario where Kepler-442b shares atmospheric components with its siblings, a celestial game of chemical tag that might probiotic compounds hopscotching between worlds. Then there's the energy balance. Tidally locked to its star, Kepler-442b likely has a permanent day side and night side. But unlike solitary planets, its tight-knit planetary family could stir the pot. Gravitational interactions might generate internal heat through tidal flexing, preventing the night side from freezing entirely. Subsurface oceans could persist across the system, linked by a network of geothermal activity. Even more intriguing, shared magnetic fields. If these planets are close enough, their magnetospheres might overlap, creating collective shields against stellar radiation, a communal defense system for potential life. Moons add another layer of potential. While none have been detected yet, the system's compact architecture makes large, stable satellites plausible. a moon of Kepler-442b could enjoy reflected light from its planet and neighboring worlds, creating a patchwork of energy sources for photosynthesis. Or consider tidal heating. Gravitational friction from nearby planets might keep lunar interiors molten, fueling subsurface oceans like those on Europa. Life here wouldn't need to rely solely on its star. It could draw energy from the gravitational symphony of the entire system. What sets Kepler-442b apart is its context. Most habitable zone exoplanets are studied in isolation, but this world reminds us that planets exist in ecosystems. A microbe on one might find its way to another via meteorite impacts, or genetic material could spread through shared comet debris. The system becomes a laboratory for cross-planet evolution, where life's adaptability is tested on a cosmic scale. As telescopes advance, monitoring atmospheric interactions here could reveal something profound. That habitability isn't just about individual worlds, but the conversations between them. While Proxima Centauri b basks in the turbulent glow of its red dwarf star, its distant sibling, Proxima Centauri c, tells a far colder and more mysterious story. Orbiting its star at 20 times the distance of Earth from our Sun, this frosty world exists in the shadowy outskirts of the system, a place where temperatures plunge so low that even gases like nitrogen freeze solid. Yet beneath its icy exterior, scientists suspect something extraordinary might be stirring. A hidden ocean, sealed under miles of ice but kept liquid by the relentless flexing of tidal forces. Proxima Centauri c is no ordinary ice ball. Observations suggest it's a super-Earth, weighing in at roughly 7 times the mass of our home planet, enough gravity to crush a human visitor under its weight. That bulk could be the key to its potential habitability. A thicker planetary structure means more internal heat, generated by radioactive decay and the constant gravitational tug of war with its star. This warmth might be just enough to maintain pockets of liquid water beneath the frozen crust, much like the subsurface seas of Europa or Enceladus in our own solar system. But here's the twist: Proxima Centauri c's ocean wouldn't be a small, isolated layer. Some models suggest it could span the entire planet, a global abyss locked under an icy shell so thick that sunlight never reaches it. Then there's the tantalizing possibility of cryovolcanism, ice volcanoes spewing not molten rock, but slushy mixtures of water, ammonia, and methane. On Earth, volcanoes recycle nutrients and gases, shaping atmospheres and climates. On Proxima Centauri c, cryovolcanoes might do the same, erupting through fractures in the ice to replenish surface compounds or even create transient atmospheres. Imagine geysers bursting into the void, their plumes freezing instantly into glittering clouds of ice crystals, a fleeting breath in an otherwise silent world. These eruptions could also ferry minerals from the ocean below to the surface, offering chemical building blocks for any potential life. The planet's extreme distance from its star adds another layer of intrigue. While Proxima Centauri b endures blistering radiation, Proxima Centauri c might be shielded from the worst of the stellar storms. Its thick ice shell could act as a natural barrier, protecting subsurface oceans from cosmic rays and ultraviolet bombardment. Life here, if it exists, wouldn't need to hide. It would simply thrive in the dark, drawing energy from hydrothermal vents or chemical gradients in the water. Organisms might resemble Earth's extremophiles, but adapted to pressures and temperatures that would instantly crush or freeze terrestrial life. Yet mysteries abound. Without direct observations of its atmosphere or surface, we can't confirm whether these subsurface oceans exist. Future missions, like advanced ice-penetrating radar satellites or probes designed to analyze cryovolcanic plumes, could reveal the truth. Until then, Proxima Centauri c remains a paradox, a world too cold for life as we know it, yet possibly warm enough beneath the ice to nurture it. This distant, frozen sibling challenges our assumptions about where life can take root. It doesn't need sunlight or a cozy orbit, just liquid water, energy, and time. and as we ponder its hidden depths, we're forced to reconsider the universe's generosity. Life might not always flourish in the light. Sometimes it thrives in the quiet dark, waiting for us to look beyond the obvious and explore the secrets buried beneath the ice. From scorching super-Earth shrouded in hydrogen haze to frozen ocean worlds hiding beneath miles of ice, these 25 alien planets redefine what habitable truly means. Each world tells its own story, whether it's the triple-sunned skies of JJ667cc, the steam-bathed valleys of Tau Ceti E, or the violent beauty of Kepler-442b weathering endless stellar storms. The sheer variety shatters our Earth-centric assumptions, proving life could adapt to environments we once dismissed as impossible. Some orbit calm red dwarfs that burn for trillions of years, offering biology an eternity to experiment. Others dance on the razor's edge of habitability, where survival hinges on thick atmospheres, tidal heating, or sheer evolutionary grit. The next chapter in this cosmic detective story is already being written. Telescopes like James Webb and upcoming missions like the Habitable Worlds Observatory will peer deeper into these alien atmospheres, hunting for the chemical fingerprints of oxygen, methane, or even industrial pollutants. Imagine analyzing the haze of K2-18b for signs of oceanic microbes, or catching the infrared glow of geothermal vents on Kepler-442b. Each discovery won't just fill textbooks, it could rewrite them, forcing us to expand our definition of life itself. But the most thrilling thought, these 25 worlds are just the beginning. For every planet we've found, thousands more wait in the darkness, each with its own mysteries. Which one captures your imagination? The tidal locked twilight of Light and Star B, the hypothetical floating ecosystems of JJ1214b, or maybe Kepler-442b, where ancient civilizations could have risen and fallen before Earth's first microbes even stirred. The universe is stranger than fiction, and the search for our cosmic neighbors is only accelerating. Stay curious, because the next big reveal could be days away. Hit subscribe to join us as we track these discoveries in real time, from the first tantalizing data to the moment we finally answer humanity's oldest question: are we alone? The cosmos is listening. What will it tell us next?